Let's now take a look at this example. In this segment here, we're going to discuss what you have learned in chemical equilibrium and kinetics could come together as a questions. So we're going to start off with this example. So where you have N2O4 converting to NO2. All right. So in this case, if I put in the reacting vessel with just N2O4, then we expect the forward reactions to be very high because there's zero number of moles of your NO2. So initially, when you first start, the rate forward will be very high and the rate backward will be very low. But as you produce more and more NO2, then the backward rate will start increasing. Eventually, when they are equal, when RF is equal to RB, dynamic equilibrium has been attained. So when dynamic equilibrium is attained, in this case itself, you will find that based on the graph, that is the graph that is actually declining for the case of N2O4, and conversely, your number of moles of NO2 graph is actually increasing. So dynamic equilibrium is attained at this position here. Next, the next things that we're going to introduce is the fact that we're going to remove NO2. If we decide to remove NO2 from the reacting vessel, you will find that now the rate backward will suddenly drop. Because the rate backward drop, similarly the number of moles of NO2 precipitously or instantaneously drop. From then, a new dynamic equilibrium needs to be attained. Since your RF is now higher than your RB, then again, positional equilibrium will now again shift forward, which means your number of NO2 will go up, and therefore the backward reaction will start increasing. When the new rate forward is equal to the new rate backward, then in that case, a new dynamic equilibrium is attained, and as you can see down here, that matches the concentration graphs that we have discussed earlier. I think finally, what is important in this example is also to note that in the exam, they do ask that if you remove NO2, what happens to the forward and backward rate of reaction at the new equilibrium or at equilibrium or when equilibrium is restored. What you need to bear in mind is that the initial rate forward and rate backward is originally at this level. But when the new equilibrium is attained, it is actually lower. So hence, when the new dynamic equilibrium is attained, the forward and the backward rate of reaction has decreased. Next part we will explain is to take a look at why equilibrium constant and positional equilibrium are not affected by the presence of catalyst. So as you can see that in the reactions where it is actually catalyzed, the EA would actually drop. And what is more critical is to take note that the forward EA actually drops by E0, and as for the backward EA, it actually also drops by E0 as well. And therefore, because of that, both the reaction forward and backward will still remain to be equal. And since they are equal, there will be no change to position of equilibrium. And if there's no change to position of equilibrium, there will be no change to the equilibrium constant. Let's now take a look at the Haber process. Let's take a look at this reversible reaction. The questions we're going to ask is that what happens if we raise the temperature for this exothermic reversible reaction? So in terms of the rate constant of the forward and the rate constant of the backward, both will increase, since if you recall back in your kinetics, in your Arrhenius equation, if your temperature actually increases, you find that the denominator becomes a smaller value. So the rate constant both forward and backward increase. And as for the Kc, since the position of equilibrium shift backward, then you end up with more reactant than product, so your Kc should drop. In line with your 1 and 2, in terms of the rate constant, if both the rate constant increases, then the rate backward and the rate forward also increases. However, you need to bear in mind that they are not equal. The reason is because position of equilibrium shift backward. If position of equilibrium shift backward, then the rate backward must actually be larger than the rate forward. Okay, if you raise your temperature, any change to activation energy? No, because activation energy is affected only by catalyst or enzyme. Finally, what happens to your percentage U? If your position of equilibrium shift backward, then of course your percentage U will drop. Okay, this is a final example where we're going to study both graphs, concentration versus time, and as well as rate of reaction versus time. In these questions, they start off with concentration of CO and Cl2 as such, and we start off with nothing for CO, Cl2, so that's the ice table. And get used to the fact that at times you might be compelled to solve a quadratic equation using your calculator, and you have to do that. So once you calculate out the value, you work out these two as the possible values, but this one is clearly rejected because it's just physically not possible for you to produce this amount, given that you are only adding 0.5 mole per dm cube of CO and 1 mole per dm cube of Cl2. Once you actually have your calculated value of your X value, you can work out all the equilibrium concentration value, and you can thereafter sketch the graphs. So in this case, the backward reaction must actually be starting off at a higher value, while the forward reaction starts at 0 because you start off with actually 0 mole of CoCl2. So in this first change that we introduce, we are making the vessel instantaneously smaller. When the volume of the vessel is made instantaneously smaller, there will be a steep surge in terms of the concentration. Bear in mind that mathematically, if the concentration originally were larger and you make a same change and you reduce the volume of the vessel, there will be higher number of moles inside. So therefore, actually this value numerically surge more than, for example, the concentration of your CO, which actually start off whereby its initial number of moles is of a lower value. So that's the first point to take note. Second point to note is that any instantaneous change always regards to volume of vessel increasing or decreasing. All right. So in this case, when the volume of the vessel actually is made smaller, clearly it favors less gaseous molecules, so position equilibrium does shift backward. If it does shift backward, then we know that your CO must actually increase. That's the dotted line in red. And as far as CO is concerned, they will both drop. Mathematically, just take note that when it drops, you will never drop below its equilibrium concentration previously. All right. So do take note of this. In the exam, they do give questions whereby they sketch a graph in this manner. This is obviously wrong. Do not pick it. Finally, I think it's also important to take note of one thing, that the time it takes for equilibrium to attain is your T1. Obviously, in this case, the time it takes for you to attain equilibrium is significantly smaller. The reason why it's smaller is because that if you reduce your vessel, obviously your reactants, your concentration of your reactant increases. That's going to increase the reaction rate. So the increased reaction rate will lead to a shorter time before the new equilibrium is being restored. Next example. Next example we look at is what happens when temperature increases. When temperature increases, given that the reaction is endothermic, the position of equilibrium shift forward. So in this case, what you can see is that the position of equilibrium, your Cl2 and your CO both increases, while in the case of your CO, it drops. In the same vein that we discussed earlier, the time it takes for you to establish its first initial equilibrium is going to be longer than the time it takes for you to establish a new equilibrium when the temperature increases, because temperature increases will favors a faster rate forward and backward.